Hi there and welcome to this video for Senior Physics on Motion. In this unit we're going to be looking at velocity and looking at how we can interpret velocity time graphs. Now we looked at in our previous post at distance time graphs and we worked out that using distance over time, or the gradient of the line, that would give us the velocity. So in this scenario what we're going to do is we're going to set up velocity time graphs. So here you can see we've got a graph which has been set up with velocity going up the y-axis in meters per second and time going along the x-axis in seconds. We've now got a straight line which is curving, which is basically moving upwards. Now we've got a straight line there, and basically from this we can work out the gradient. Now the gradient of a velocity time graph is going to equal our acceleration. Now remember, our gradient is made up of our change in velocity over the change in time. We call this the rise over the run. Hence from this we get the algorithm that acceleration is made up of change in velocity over the change in time. So we need to remember that definition. The definition that we learnt in our very first video on terms has now been incorporated into a mathematical relationship. And that mathematical relationship comes from observations which have then been plotted on the graph. So hopefully you're able to see that the graphs are really important when it comes to determining or coming up with a mathematical relationship which we can utilize in physics. So be warned that when you study physics, a lot of the things that we use, the equations that we use, have often stemmed from observations, and then they have been graphed, and then those graphical relationships have been converted into a mathematical relationship, which are the equations that you use every day. Now in this graph we can see that we get a straight line which is rising upwards away from the horizontal, and this means that we are accelerating at a constant rate. This means that the speed is changing at a constant rate over time. Now let's look at a couple of other graphs and try and determine what that is happening in each of those cases. In this case we've got a horizontal straight line. That means that the velocity is actually keeping at a constant level. It's not changing. If we've got no change, then hence we've got no acceleration. So a horizontal straight line will give us a constant velocity, hence no acceleration. Now if you remember back to our distance time graphs, a straight line basically meant that we were stationary, we weren't moving at all. In this case, it's determining that our velocity is constant. Let's look at this graph. In this graph, the line is actually sloping straight downwards. What this means is that the velocity is actually decreasing as time goes on. Hence we get a deceleration, or a negative acceleration if we use vector notation. And we'll be looking more about vectors later on in this unit. So if the curve is sloping straight up, then we've got a constant acceleration because our speed is increasing. If we've got a horizontal straight line, our velocity is constant and no acceleration. And if our curve is moving straight downwards, then we've got a constant deceleration as our velocity is decreasing. So let's put all this into practice. So here we've got a graph which is rising at point 1, is flat at point 2, and then is curving down at point 3. And then we've got number 4, which we'll look at in a minute. Well, 1, as we've already determined, shows that we are increasing our velocity, hence we've got an acceleration, a constant acceleration. In 2, we've got a constant velocity, which means we have 0 acceleration, and in 3, our velocity is decreasing, so thus we've got a deceleration, or a constant negative acceleration. Now what 4 represents is the area under this line. Now the area under this line will basically determine the distance travelled. Now you may ask, well, how does that come about? Well, let's put it all together and look at the equation that will allow us to work this through. So the area under the graph is basically the base times the height. Now the base is obviously in seconds and the height is going to be in meters per second. So let's put those units together and see what happens when we solve them algebraically. So we'll put our units down. So along the base we've got our time in seconds, and we're going to multiply that by our units for velocity, which is in meters per second. So it's s times m over s. Now the two s's cancel out, which leaves me with just meters. Hence the area under a velocity time graph is going to be our distance in meters. So again, you can see that we've got our graph which has been utilized to determine a variety of different things. Graphs are really, really useful, and as a result, as physicists, it's really important that you get to learn them. Okay, so let's have a look at an example. We've got a graph similar to the one that we used below, but with a few more units on, of a train going between two stations. From this, we're going to find the acceleration, the maximum velocity, the retardation or the deceleration, and the distance traveled. Okay, pause the video now, see if you can solve it, and then come back and we'll run through the answers. So pause it now. Okay, welcome back. So how did we get on? So let's look at the acceleration. Well, we're talking about acceleration, which is a positive acceleration. So basically that's going to be the first line in our graph. So basically what we're going to look at is the change in velocity. Now change in velocity is basically going to be 30 divided by the time 20, which gives us 1.5 meters per second. Now basically what we did there, the change in velocity was 30 minus what we started at, which was 0. So for change in velocity, we can always work this out by doing our final speed minus our initial speed, and that will always give us our change in velocity. Again, we'll study a bit more about that later on in this unit. Now let's look at the maximum velocity. Well, reading off the graph, the highest velocity it ever gets to is basically 30 meters per second, as can be shown by that dotted line, that horizontal dotted line. The retardation is going to be the third portion of the actual graph. This is the slope going downwards. So we look at what we start with, which is 80, and then we're going to take away what we look at what we finish with, which is 80, look what we start with, which was 30, we take the 2 away, 80 minus 30 basically is going to be our 50 meters per second, and that happens over 30 seconds. So basically we're going to solve this, and the result is that we get minus 1 meter per second. So the retardation is 1 meter per second, or it's a minus value if we're talking about acceleration. Because acceleration, we always say positive is going upwards, negative is going downwards, it's a vector. Again, that will make more sense when we look at vectors later on. Now the distance traveled is going to be the area under the graph. So what we have to do is to look at and split them up into various sections. We've got a triangle followed by a rectangle followed by another triangle. So work out the area for each, and we end up with 1,650 meters. Now you will notice that a velocity time graph basically gives us a lot more information. So it's important that you're able to go through and interpret this graph and be able to utilize the various portions of this graph later on. Okay, so I hope you found that useful. Do go and check out the worksheets that I provided on this post. Have a go at them, and if you have any questions, by all means you can email me or ask your teacher. Well, that's all for now. Thanks for watching, and I look forward to you meeting me again.